Okay, well, yeah, we're going to dive into a little bit more of this V to Q ratio thing here. Um, and then we'll get into kind of gas transport, gas exchange a bit. Yeah, that'll be most of it. Um, yeah, so we left off with this last time. Let me get the little light, my favorite light situation. There we go. Okay. Um, yeah, we left off with this last time, looking at these kind of three possible scenarios of this V to Q ratio, right? The one in the middle kind of being normal, where we have good blood flow through the capillaries and we have full ventilation of the alveoli, right? That's kind of the ideal situation where we can fill up the red blood cells with oxygen, right? The one on the left there, when V to Q ratio is greater than zero point 0.8, is we don't have the blood flow that we need, but we have plenty of air getting into the alveoli, right? So that can lead to some desaturation, right? Lead to a lot of desaturation if there's no blood getting through. And then the one on the right is the opposite. When the V to Q ratio is under zero point 0.8, then we're not getting air into the alveoli or enough air into the alveoli, but we have plenty of flow through the capillaries, right? So those are kind of our three options. Okay, so let's look at that in terms of the idea here is that depending on where you are in the lungs, the V to Q ratio isn't the same because of the effects of gravity on blood passing through the capillaries. Okay, and so this little thing that kind of looks like a little rocket ship or space shuttle is the kind of way that the lungs are represented here. And so we can kind of walk through the different things here. So there's three different abbreviations there. Okay, and you can see the definitions of them over here. Okay, and so the P with the little a is the pulmonary arterial pressure. Okay, so that would be um, the pressure of the blood getting pushed into these little arterioles. Okay, so this is kind of representing the lung, right? These little vessels going through are the little capillaries. Okay, and then all around it would be kind of the space that the air pressure was creating around the capillaries. Okay, and so the P with the little a is the pressure of the blood pushing into those vessels. Okay, so that's the pulmonary arterial pressure. Okay, the P with the big A is the alveolar pressure. So that's like the pressure of the air around the capillaries and what effect that has on the capillaries. Okay, and then the P with the small v is the pressure on the other side of the capillary bed. Okay, over here on the venous side. Okay, so those are the three things to think about. And so we'll start kind of at the top part of the lungs. Okay, so it's the top, the one corresponds with the one up there. Okay, and so the alveolar, sorry, not the alveolar, but the arterial pressure, the P with the little a, is going to be the lowest up here because it's hard to get blood up there, right? It's hard because the heart is pumping the blood up this way through the pulmonary arteries, right? And getting up here, and not as much blood gets up to this spot, right? Because of the effects of gravity, we're trying to get the blood up there, but not as much ends up getting up there. So the pressure that we create in those pulmonary arterioles is not as high up in the top of the lungs. Okay. But the pressure in the air pressure around is still high. Okay, we're filling up the alveoli to their max there. Okay. And then the pressure on the venous side is very low as well, even lower. Okay. So what ends up happening in the very top part of the lungs is those pulmonary capillaries just collapse because of the pressure of the air around them. Okay. So we're not really able to get much blood through that spot at all. And that's kind of the very top portion of the lungs. Okay. Uh, then we go to the middle part. Okay. So this will be kind of level with the heart. So the heart is kind of just pumping the blood directly in that direction. Okay. The pulmonary arterioles here is kind of a mid-range pressure. Okay. So we can kind of say mid. Okay, the pulmonary the alveolar pressure here is kind of low to mid. Okay, and then on the venous side, we have the pressure is still pretty low here. because you can kind of see that the water, or not the water, we'll say the water in a sec, but the blood isn't filling up that venous side very much yet, right? So pretty much what ends up happening is the vessels kind of smash down a bit, but blood's still able to get through. Okay. And so what it creates is this kind of waterfall effect where blood is pushing through. And when it gets through this smash down part, then it kind of shoots here and falls down this spot because it's not like the venous capillaries or the venous side here on the other side of the capillaries is full of blood. So the blood just kind of falls down. It kind of creates this waterfall effect as it pushes through that smash down capillary and then falls down into the kind of place where the blood is pooling a bit on the other side of the capillary bed low in the lungs. Okay, so that's kind of that one. And then we get down to the bottom section. And so the bottom section, the pressure in the arterioles is high here. Okay, this is kind of below the heart, right? So the heart's pumping blood this direction, and now it has the gravity helping it make the blood flow into the pulmonary arterioles here. Okay, and then and then here we kind of have mid to high pressure, and then on the venous side, we have oh sorry, I did the wrong one there. This one, the pulmonary alveolar pressure is low here, and this one is kind of mid to high. Okay, because blood is pooling a bit and in the venules over here, right? We got lots of pressure here, so it actually extends, stretches out the capillaries a little bit because the air pressure around them isn't as much. Okay, and so that's kind of the effect there. And so this is just something to think about when there's patients with pulmonary issues, right? And one of the main reasons it's so helpful to have a patient kind of lay down in a reclined position is because then you're kind of activating more of the upper parts of the lungs. We can start using the upper parts of the lungs more in that case, right? And so when a patient lays down, all this is kind of shifting. We're increasing the capillary pressure, the arterial pressure in higher regions of the lungs, so we can start kind of perfusing the top part of the lungs better. And that's what that semi-reclined position is kind of all about. So yeah, so what I want you guys to do next is take this information and kind of connect it to what we were just talking about with this ventilation versus perfusion ratio, okay? And do that here with this next thing. So this is kind of the same idea here, right? These should pretty much match what we were just talking about, okay? And so what I want you to do is, what would the V to Q ratio be with each of these? Okay, so ventilation, V is the air part, right? Q is the blood flow part, right? And so take a guess on what you think with each of these. Where would these be in relation to 0.8, right? 0.8 would kind of be the mid-range where we got good ventilation and good blood flow, right? So what you think it would land right around there? You think it'd be above that or below that? Okay, so take a sec and see if you can kind of interpret that, and we'll come back together in a sec.
Like say during a sympathetic nerve or sympathetic nervous system like activation, would you'd see more vasal constriction, so then would you get more blood to just more parts of your lung then like to the upper
You would have more flow. I don't know if you would vasoconstrict your pulmonary arterioles. It might be one of those areas that kind of does the opposite,
Okay.
like with under sympathetic control. That would probably be my guess. I don't know that for sure,
Yeah.
but we would have, yeah, more ventilation, right? Because more air coming in, so then the alveolar pressure would increase. And so we would probably dilate some of those to be able to increase flow as well. So to kind of match the alveolar pressure would be
So
my,
you get
would be my
more
guess.
efficient blood.
Yeah.
Yes, because then you'd be able to use the other lobe.
Yeah, you'd kind of expand the area that's perfusing well because of the extra blood flow, the increased cardiac output to the right side of the heart. So, we don't normally talk about right side cardiac output, but that would have to increase as well. Yeah, so, yeah, cool. So at least get to the point of just making a decision on that V to Q ratio for each one. You think it's right at 0.8, you think it's above, you think it's below. Those are your three options.
That are written out already.
Yeah, the abbreviation slightly different, huh?
Is this at the highest? I thought that's at the lowest.
Which one? So P, that one on this, the
PPA.
PA there is the same as the little a on the previous one. That makes sense?
So it's talking about that.
Yeah.
Oh,
Yeah, I know the abbreviations were mixed on that image that I found, yeah. Yeah.
Whoa, alveolar pressure. So it's
Yeah.
like,
It's like the air around the capillaries.
and then these two, so these two are more to do with the blood pressure. Like in the artery.
Yep, exactly. Yep, exactly. And think about like the capillaries are just like on the alveoli, right? And so when those alveoli expand, that actually can smash down the capillaries a little bit. Yeah. Yeah.
Oh.
Yeah.
I'm just getting a little confused on the
Yeah.
abbreviations.
Yeah, they switched from slide to slide.
Okay,
So
so
the
this is-
little a matches the PA on this.
So that's
that one.
arterial,
Yeah,
and then okay.
the other ones are the same, but
Okay.
yeah.
I'm just confused on why the P big A,
Uh-huh.
why that changes.
Yeah, so think about like like if my hand, my fist is an alveoli, right? And we have these capillaries like surrounding them. Like when we fill those up a lot, it's actually like putting mechanical pressure on those capillaries and can smash them down.
That makes sense. Then once there's more blood, then it like, I don't
And
know.
it can kind of fight against that, yeah, because it's stretching, the capillaries are stretching too, yeah.
But thank you.
Yeah. Oops, sorry about that. All right, let's go ahead and come back together here. Okay, one thing I need to fix on the slides, but with this image that I found, I liked it, but except the abbreviations were just slightly different, right? So this PA one is the same as the P little a one on the previous slide. If that makes sense. Okay. So that's the arterial one is represented by PPA on this slide, whereas the previous one was just P little a. Okay. Okay, so let's talk about the VQ ratio thing first. And so, yeah, so with this one, which pressure is the dominant? Is it the pressure of the air in the alveoli? Is it pressure of the arterial, the blood in the arterioles, or the blood in the venules? The air, right? The air is the dominant one here because it's hard to get blood up here, right? And by the time the blood gets up there, it's lost a lot of its force, right? So we don't have a lot of pressure getting it all the way up there, okay? And so if you think about it this way, if you think about my fist as like an alveolar sac, right? And we've got all these capillaries surrounding those, okay? Like my other hand is the capillaries, right? When we fill up that alveoli with a bunch of air, it's literally putting mechanical pressure on those capillaries, right? It's like smashing down the walls of those capillaries as we do that, right? And so that's what's happening here, right? We've got this mechanical pressure of the air kind of expanding out, and the capillaries are just linked right to that alveoli, right? So it starts smashing down those little vessels, right? And so we have dominant pressure with the air here, which is greater than the blood pressure we're creating to get the blood through the capillaries, right? Which is way greater than the pressure over here on the venous side. Okay, so what did you guys put for the V to Q ratio here? Greater. So yeah, that would be like which one here? Like A, right? In this one? Yeah, where we have plenty of ventilation, right? We got plenty of air coming through, but not enough blood flow, right? So yeah, so on this one we would say the V is way greater than the Q, right? We would say this V to Q ratio is not equals, but greater than 0.8. Yeah, so this, there's no perfusion in this part of the lungs, right? This is a very small part of the lungs, like the very top of our lungs, where we don't really get perfusion, right? And so you might think like, well, does this make it so we don't fully saturate our blood, right? Well, if there's actually no blood getting through, then that's not really much of an issue, right? Because we're not sending blood through that's not getting saturated. It's just not actually getting through, right? But this is kind of a small part of the top of our lungs, right? And then here, we've got a little bit more of a balanced situation, right? So we've got the pressure in the arterioles being a bit greater than the air pressure, that alveolar pressure, right? Which is still greater than the venous pressure, right? So we have something closer to a V to Q match, right? So something a little bit more like that, right? But we won't say exactly equals. That's supposed to be one of those signs. Sorry, that's really bad. Let me try that again. Then it does that. Um, you know what I was going for, but it wasn't working. Like that. There we go. Okay. Something a little bit closer to that. Not exactly though, right? Because we're talking about it being kind of closer to 0.8, right? So kind of equivalent to 0.8. Still haven't struggled with that with that squiggly line, but okay. So yeah, something a little bit closer to 0.8. So in this case, and this is the vast majority of the lungs, right? This is kind of the whole middle section of the lungs, right? And so we got good perfusion. We have good filling of our red blood cells here with oxygen. And this is, again, kind of the vast majority of that big swath of the middle of the lungs. Okay. And then that last part, we have Q being greater than V, right? So we have like too much blood pressure. The blood actually goes through the capillaries almost too quickly. And we don't have enough time to necessarily fully fill it up. And so then our V to Q ratio could be down in this part a little bit less than 0.8 here, right? Because we kind of have too much blood flow for the amount of ventilation that we have there. Okay. And so a couple kind of connections to this would be number one would be in some real kind of high level endurance athletes, we can see during a maximal exercise test in elite athletes that have VO2 max values of like 70 plus, and then even in those, it's only maybe about 20% of those. We can start seeing their blood desaturating when they get close to maximal exercise. And one of the reasons for that is that their cardiac output from the right side of their heart is so massive that a larger swath of the lungs does this right here. And we're pushing blood through the capillaries too rapidly. So we can't actually fill up the blood. And so we start seeing some desaturation in those athletes when they're getting close to maxing out. And so the other kind of extreme example of this is in racehorses. Like these incredible athletes that are racehorses, they have VO2 max like some of the highest VO2 max values ever recorded in humans is maybe around like 7 liters of oxygen per minute. These racehorses are somewhere around 80 liters of oxygen per minute, and their cardiac outputs are somewhere around I think of somewhere like 400 liters per minute, where humans are like somewhere around 36 to 40 liters per minute. The problem with that is, if you've ever seen videos of this or things, they don't show you, you don't get to see the horses when the race is over, because a lot of them are coughing up blood, right? Because their hearts are so powerful that they're just bursting a lot of their capillaries in their lungs. So it's not just distension of these capillaries, but literally just bursting their capillaries in their lungs, and they're literally just coughing up blood. There's blood just pouring out of their mouths a lot of times after the race. So yeah, there's a part of the controversy around that is related to that. So yeah. So yeah, this is a real thing that we're literally stretching out these capillaries here, right? Then over here, we're literally smashing them down. So yeah. Yeah, questions about that? Okay. Yeah. The other, I guess the one other application I'll mention on this would be with exercise. We, number one, we increase our cardiac output, right? Not just on the left side of the heart, but we increase our cardiac output on the right side of the heart. And so what that means is we're able to tap into a larger part of the top of the lungs, right? Because we're sending in high pressure flow. And so the point at which these capillaries get smashed down is less, right? It's going to be higher up because we're sending in more blood, because our heart is pumping harder, right? So we're able to create more pressure over here and push that blood up higher, right? So that's one thing to think about. And we are breathing more too, right? So we're ventilating more as well. So then some of those pressures are going to increase. So we're kind of trying to, tap into more of the lungs by sending more blood there, but also fighting against that extra pressure by the air as well. So kind of just some different dynamics to think about with this. So, yeah, questions about that? All right. Okay. Well, let's talk a little bit about oxygen transport. And so oxygen transport in the body is pretty simple compared to CO2 transport. We'll talk about CO2 a little bit next week, but oxygen transport, almost all of it is carried by our hemoglobin, right? So 98.5% is carried by hemoglobin. So it's a very efficient system. A lot of resources in our body are dedicated to this, right? We have about 30 trillion cells in our body. Of those 30 trillion cells, 25 trillion are red blood cells, right? So this is like a massive production that our body does, right? And then that means we only need to carry about 1.5% of this in the plasma, right? So gases can dissolve into water, right? And that's kind of what this is. When you hear about like hyperbaric treatments for healing of injuries and things like that, we're not changing that part that's the amount of oxygen that's in our red blood cells. We're only changing the amount of oxygen that's in our plasma, right? So increasing barometric pressure around the body pushes more oxygen into the water part, into the plasma, but it doesn't really have any effect on the red blood cells. So there are some times where those treatments are helpful, but we're already carrying the vast majority of all the oxygen we can in our red blood cells. So we're just kind of bumping that up a little bit with hyperbaric treatments, but not a ton. So CO2 is a bit of a different story, right? About 70% of it is carried in the form of bicarbonate. Okay, we'll talk about that and walk through the chloride shift thing next week. About 20% of it is in hemoglobin, and then about 10% of it's dissolved in plasma. So quite a bit more in plasma. And this equation is key for that, right? We've seen this equation before, the bicarbonate buffering system. Yeah, we'll dive into that more next week when we look at the carrying of CO2. But okay, so before we kind of dive into this, it's really important to understand what it means when we're talking about a partial pressure of a gas. Okay, so partial pressure is the way that we'll measure concentration of gases in our blood. Okay, and so the idea of partial pressure is that we take the full atmospheric pressure. Okay, so like kind of normal sea level pressure is about 760 millimeters of mercury, right? This is like pretty much the equivalent of the weight of all the air molecules from the atmosphere to our heads, right? So it's like how much stuff is above us, and it's like the weight of that, right? So that's like the weight of that on our heads. That's atmospheric pressure, okay? And then when we talk about partial pressure, what we want to know is of that total weight, how much of that is accounted for by each of the gases in that air, right? And so with nitrogen, that's by far the most prominent air molecule in our air. That's 78.6% of it. Oxygen's about a little bit under 21%, and CO2's very low, about 0.04. Okay, this is a simplified version. Obviously, there's more things in our air than just these three gases, but we'll use these percentages to help us. Okay, so really we can calculate partial pressure here, right? If we have it, we've got our atmospheric pressure here at sea level, and then the most extreme place on planet Earth, Mount Everest, right? So that pressure drops to 253 millimeters of mercury at the top of Mount Everest, okay? So just go ahead, pull your phones out or whatever, do a quick calculation of these. So the way you calculate this is you take your total atmospheric pressure, multiply it by the decimal version of these numbers, right? Which just means we move the decimal place to the left with each of these, right? And then you should be able to add those three percentage or those three partial pressures back up, and you should get 760 if you did it right. Okay, so just try that briefly, and then we'll talk about why this matters in a sec. You guys can check with each other, make sure you're on the same page there when you get those calculations. Had Michael do it. Yeah, good, great. That's awesome. Really, you're like, I gotta do that soon. Yeah. Hmm. Wow.
We had so many things to talk about.
That's really cool. Yeah, fun. Inspirational, maybe, instead of intimidating. All right, you guys got this? Good. Math in the morning. Problematic for sure. Okay, let's walk through it. So we're just taking the 760, times it by 0.786, times it by 0.209, times it by 0.00004, I think, right? If I said the right number of zeros, but yeah, so we get something like this, right? So we get about 597 millimeters of mercury of nitrogen, about 159 millimeters of mercury of oxygen, which is a pretty normal number that we'll see, and then about 0.3 millimeters of mercury of CO2, right? And so this is the most standard way to measure concentration of gas in the air or concentration of gas in a fluid as well, okay? So this will also apply to the blood, okay? I'll talk about that in a sec. So then if we shift to Mount Everest, right, then we're a lot lower, obviously, okay? We've only got, we have about a third of the concentration of oxygen at Mount Everest that we did at sea level. Okay. But the percentage is the same, right? So that's the whole thing, is the percentage is the same. It just means that the molecules are way spread out, right? That's all it is. They're still the same, still 20.9% oxygen, but they're just super spread out now. They're not as condensed as they were before, right? So yeah, so that's going to be the major effect that is problematic for us at altitude, right? Is that fact that we just have way less oxygen in one given little space, right? And that's going to be the problematic thing. So questions on the calculations at all or the concept of that before we move on? Okay, so then when we look at getting oxygen from the air down to our mitochondria, the key thing is we need a downward step in partial pressure of oxygen every kind of passing point of oxygen, right? Every place we need to send the oxygen from one part of our body to another or one structure to another, we have to have a downward, we have to have a decrease in the concentration gradient, right? That's what this is. It's all about concentration gradient, right? So at sea level, we're going from inspired air down of about 150 down to our alveoli of about 104. Why does it decrease when we get to our alveoli again? Remember? Yeah, Kyle? Perfect. Yep. It's that residual volume, right? We have air sitting in the bottom of our lungs that we've already exchanged the oxygen from it, right? So we're kind of mixing the new air with the air that's already been down there, right? Then we still need a drop to get the oxygen onto our blood, right? Then the kind of the hardest part to get oxygen through is through our interstitial space. So now we've gotten the blood cells down to our capillaries, right? But then there's this space, but there's a capillary here, right? There's a little bit of space, and then there's a cell we need to get it to, right? But that space in the middle, that interstitial space is typically kind of the hardest place to push it through because there's no special carrier there, right? It's just dependent on concentration gradient. So we have a big drop there, right? That helps us push it through better. And then dropping down to the cells, our myoglobin, and then to our mitochondria, right? So if we kind of filled this in for Mount Everest, we could kind of just guess at the numbers here, but this dropped by about 1/3, right? So maybe we'll say something like, I don't know, 35 or something, right? This one dropped by just a little bit, so we'll just say like 33. This one dropped by more than half, so we're down to like 15 now, right? This one dropped by half, so we're down to like 7 now, right? This one dropped again by half, so now we're down to like 3, right? And now we have a much smaller gradient to get down to our mitochondria, right? Um, and so the bottom line is that just means a lot less oxygen is going to get to the mitochondria when we're at altitude, right? So much less oxygen gets to so this is the tough part of about moving and exercising at altitude is we just can't use our oxidative system as much because we don't have as much oxygen available in our mitochondria. Okay. Questions on that concept at all? Yeah, Tesla. It does, yeah. So because of this right here, the amount of oxygen in our blood, the saturation in our blood is sensed by our kidneys, right? And then our kidneys release erythropoietin. Erythropoietin is a hormone that goes to our bone marrow and stimulates red blood cell production, right? And so this is what athletes are going for when they go to altitude to train and stuff, right? They're trying to bump their red blood cell count up. But it takes a while. I mean, it takes really to have the effect of that. It takes like at least a month to kind of do that whole process. So it's not something that happens quickly. But for example, people that live at high altitude, like people that live in the like the Sherpa people that help people get up and live in the Himalayas and help people get up Mount Everest, help all the people that spend like $30,000 to $40,000 to hike Mount Everest is what it costs. They're paying these people to carry all their stuff for them, right? Because they can't carry it themselves. But literally, you see like pictures of these people that just have these giant like their whole backs are just covered in all the stuff that they're carrying for these people. But the Sherpa people have like it's somewhere around yeah, like like our typical hematocrit's like 45, right? The typical hematocrit of that group of people is like 52 or 53 or something, right? So just way more red blood cells just naturally, which does make your blood a lot thicker and makes it so it's harder to move through your vascular system. But yeah, so definitely that's kind of like long-term effects of that. But yeah,
Do
Andy.
you have to train at altitude altitude for all of that month, or can you train for 1 or 2 weeks and then you'll get the effect?
Yeah, the kind of the main way to think about it is actually going to altitude to train is not the best because you can't push yourself as hard. And so there's all this kind of research around like, is it better to live high and train low, or live high, live and train high, right? And it's probably better to live at high altitude, but then train at sea level because you can push yourself to a greater degree and you can get that same stimulus, but then you can get the stimulus of the low oxygen content, which bumps up your red blood cells while you're sleeping. And so that's why like Olympic athletes will have like hypobaric tents they sleep in and stuff like that. Just like in their room, like a little tent that makes it like, so they got less oxygen they're sleeping with, just kind of doesn't sound very, very comfortable, but that can stimulate the red blood cell production. And then you can train as just as hard as you could, so yeah.
The Inuit tribes in northern Canada, they're found to have like twice as many capillary beds in their hands and feet.
Mm.
Like the lower perfusion is twice as likely to get.
Who did you say in northern Canada?
The Inuit tribes.
Oh, Inuits. Yeah. Okay. Yeah. Interesting. Yeah. Because of the cold exposure more probably, or is that what?
Cold and just oxygen. It's like because they live like it's really high altitude.
It is high up there too. Okay. Okay. Yeah. That's cool. Very cool. Yeah. Other questions or comments? Okay. All right. So, yeah. So the bottom line here is both oxygen and CO2 have to have a gradient to move, right? And so, yeah. So when we look at this image, this is showing both oxygen and CO2 and where they move, right? And so, yeah. So when we look at this, we can see that alveolar O2 pressure here, lower than atmospheric. That was one question we just talked about. And yeah, I think I'll let you guys kind of talk about this for a sec. These two slides here just have a couple questions for you. We've already dealt with a couple of these, but just go ahead and kind of walk through these three questions here, and then here. This is one that I just drew, but you can kind of write in here. You're kind of just filling in either high or low for each for both CO2 and oxygen. And then it's kind of these questions of where does CO2 enter the blood? Where does it leave? Where does oxygen enter? Where's oxygen leave? Okay, so yeah, kind of walk through these, interpret what's going on with the numbers here on this one, and then just kind of here on this side and answer those questions. We'll come back together in just a sec and make sure we're on the same page. Okay, go ahead. All right. So Hannah, you're like the team mom back there with all the snacks back there. Yeah. Uh-huh. You got snacks, yeah. That's amazing. Class mom, Hannah. That's awesome. Yeah. All right, well, let's walk through these questions here together. So this question we kind of already dealt with, but what would be the answer to this? Why is alveolar O2 pressure lower than atmospheric? What was the answer for that again? Residual volume, right? Yeah. So the air's got to mix with residual volume. Okay, we'll deal with this on the next slide. And the bottom line here with altitude is we're changing this number, right? Changing that number, which then means we got to change this number, which means we got to change this number, and we got to change them all, right? They all have to drop in order to let oxygen move, which in the end means we've got to change the amount of oxygen in our cells, right? And that's what makes it so we have a lack of oxygen get into our cells. Okay, but yeah, let's walk through this one here. So if we're thinking about the heart here, right, getting our blood, pumping that deoxygenated blood to the lungs, it gets filled up, right, through little pulmonary capillaries here. Now we got oxygenated blood getting back to the left side of the heart, out to our tissues. We're going to do our oxygen or gas exchange here, back to the heart, right? So that's the idea, okay? So we can start over here on the pulmonary vein side. What did you put for CO2 there? High or low? Over here on the pulmonary vein side? Low. Yeah, be low because we've already dropped off the CO2, right? What we put for oxygen there? High, okay, because we got fully oxygenated blood. Okay. Same thing with systemic arteries, right? Because we've all we've done is taken the blood and gone to the left side of the heart and then pumped it out. We haven't done any exchange with it yet. Okay. But now we're getting down to the tissues, right? Just general cells we're trying to get oxygen to, right? So the oxygen here and CO2 here in the cells themselves. What'd you put for CO2 there? Probably higher, right? Because this is where metabolism is happening, right? We're building up with a byproduct of metabolism, which is CO2, right? And then we're going to have low levels of oxygen there, right? Which is what allows oxygen to move from high to low, right? And then that allows CO2 to move from high to low as well, right? So CO2 is entering the blood down there at the tissues. All right, so CO2 is coming from the cells that are doing metabolism and using up oxygen. CO2 is getting pushed into the capillaries here. So now we're into the systemic veins. Okay. Those systemic veins, what'd you put for or for CO2 there? Now it's high, right? Because we added CO2 to the blood at the cells, right? And then oxygen, low, right? Low because we dropped off oxygen at the tissues, right? Because we went from high to low here, right? To push that oxygen into the cell so we could use it, okay? And then now we're back up to so now we went to the right side of the heart, right? Pump that blood out of the right side of the heart over to through the pulmonary arteries to the lungs, okay? And so the blood is still going to be like this, right? High CO2 and low oxygen, but now the lungs, we need the lungs to be the opposite of those two things so we can move the two gases, right? So CO2 levels are going to be what in the lungs? Like we're talking about inside the alveoli, right? Should be low, right? Yeah. We should have low CO2 levels with that fresh air that we got down from the atmosphere, right? And then oxygen levels should be high, right? So then we're moving CO2 from the blood here into the lungs, right? We're moving oxygen from the lungs into the blood with those concentration gradients. Okay, so CO2 is leaving the blood. Where? What'd you put there? The lungs, yeah. Lungs, and then oxygen enters the blood, obviously at the lungs, and oxygen leaves the blood at the tissues. Some of my best artistic work right there. I'm serious though. I'm really bad at drawing. So. Okay. Questions about any of that? That makes sense? Okay, well, let's talk a little bit about the oxygen hemoglobin dissociation curve. I know at some point in biochemistry, you guys kind of dissect this a little bit with hemoglobin. Have you already done that? Yeah, good. All right. So that's some good background for this. And have you already do you actually look at this curve itself? Yeah. Yeah, good. Awesome. Okay. So that's super helpful, right? So we've got down here is partial pressure, right? This is what we're talking about this whole time. This is just concentration of oxygen around the red blood cell, right? How much oxygen do we have around the red blood cell? Okay, that's the x-axis. Y-axis is based on that concentration of oxygen. How much of it gets pushed into our red blood cell? What percentage of our red blood cells get filled up with oxygen, right? And so, yeah, so that's our starting point there, right? So then when we look at this curve, we've got kind of different aspects to it that can be really helpful for us, okay? So if you look at the kind of the numbers in here on the top part, right? So where in the body and on the curve is the plateau, right? We have this kind of flat part of the curve here, right? It's pretty flat. That's kind of the plateau part. Okay. So if you go back to this image here, and we look at these partial pressures of about 104, right, in our alveoli, right? If we're at sea level, if those numbers are similar to this, if the amount of oxygen we get down there ends up being about 104, then that pretty much means that we're going to fully fill up our blood, right? Because we're all 104 would be like all the way out here, right? So we're hitting there. But then up to certain altitudes, this partial pressure is going to start dropping a little bit. But even if it dropped all the way down like 20 millimeters of mercury, even to 80, we'd still pretty much fill up our blood all the way, right? That's the benefit of this plateau, is that over a pretty large range, right? Somewhere from about 20 or about 20 millimeters of mercury, so like 80 to 100, we still pretty much get fully saturated, right? And that's just the properties of this protein, right? That within this range of concentration of oxygen around it, it's still going to grab onto oxygen to pretty much its full extent. Okay, so this is going to happen at the lungs, right? Is where we're going to have partial pressures around this range. So where in the body is it, and then where on the curve is it? Just obviously like the right side of it, right? But probably somewhere between about 80 and 100 plus millimeters of mercury is where that's going to be, right? So we have this pretty good sized range at the top where we're going to fill up our blood no matter what, right? So that plateau is super helpful for us there. Okay. Yeah, going to fill blood over a large range of oxygen concentrations. Okay, so that's kind of the right side of the graph is kind of showing us that, right? This graph over here is kind of highlighting the steep part instead, right? So now this steep part pretty much ranges between, kind of really starts dropping off at around 40 millimeters of mercury. And it's steep throughout that whole section, everything to the left of that, right? And so if we go back to our numbers again here, where do we see a number that lands around 40? The interstitial space, right? Interstitial space right here is about 40, right? So that makes perfect sense that that's the way that this protein is going to be designed. So because that's about the partial pressure of oxygen in our interstitial space when the oxygen needs to leave our blood and make it through this kind of no man's land to get into cells. All right, it's got to go through this interstitial space. And so we see that very steep part of the curve starting right about 40, okay? What would make that partial pressure of oxygen get lower from 40 right here? Besides altitude, what else would make this drop to like 35 or 30? Talk to each other about that for a second. Why do you think that would happen? Besides altitude. All right, what do you guys think? Somebody raise their hand, what would make it drop? So we know altitude would make it drop. What else could make that partial pressure of oxygen in interstitial space get lower than 40? Any thoughts? Exercise, yeah, any increase in metabolism, right? If we're using up more oxygen in our cells, that makes that mitochondrial number drop, which makes this number in our cells drop, which makes this one drop as well, right? Because we're keeping up that we're just creating a stronger concentration gradient by using up oxygen in our cells, right? Which then can make each of those numbers drop a little bit, right? So if this number drops from 40 to 30, what does that do here, right? Oops. Instead of being saturated at about 75%, now we're saturated at about 50%, right? So we went from 75 to 50%, which means we dropped off 25% more oxygen. Okay, so in a pretty small range, a pretty small change of oxygen concentration that we can elicit by using up oxygen in our cells, we drop off way more oxygen, right? Because the curve is so steep right here, right? If it was flat here, it wouldn't do that, right? If it was flat there, it wouldn't change how much oxygen we dropped off. So this is why that's really helpful, right? So this would be down at our cells, right? Interstitial space. Okay, why is this beneficial? Because for an increased metabolism, we'll say for a small increase in metabolism, we have a large increase in oxygen delivery. Right, so we increase our metabolism a bit enough to drop the amount of oxygen in the interstitial space, and that makes our red blood cells drop off a lot more oxygen, which is exactly what we need, right? Because we need more oxygen if we're using up the oxygen, right? And so yeah, so that helps us a lot. Okay. Questions on that? That makes sense? I just said for a small increase in metabolism, we get a large increase in oxygen delivery. Okay, altitude's a problem. We've kind of already gone through that quite a bit because we're just decreasing the amount of oxygen overall that gets into our cells. And at real high altitudes, we're moving out of that plateau, right? We said that let's go back to our oxygen cascade thing here, right? So instead of being at 95 in the blood, we're at around 35, maybe 33. Okay, let's look where we would be there. If we were at 35, that's pretty much where we just drew the line, right? So normal oxygen saturation at the top of Mount Everest, if you're not using supplemental oxygen, would be somewhere around 50 or 60%, right? So you put an O2 sat on somebody's finger, and they're fine. That's a healthy number. That's a healthy number at that level, right? If you get that in your patient, you'd be very concerned, right? But that's normal at that level. So, yeah. Okay. All right. So then the other thing to talk about here is moving this curve, right? Shifting this curve. And so the blue line is kind of representing no shift of the curve, right? The red line is what we call rightward shift. Green line is what we call leftward shift. Okay. And there's pretty much four things that lead to a shift in the curve. Okay. One of those things is pH. Okay. Another one of those things is CO2 levels. Another one of those things is temperature. Okay. And then the other one is, I think I have it on this one. Yeah, right here, this 2,3 BPG. You guys probably talked about that one in biochemistry. Yeah, yeah. So these are all byproducts of metabolism, right? That's what they are. We increase CO2 when we're doing more metabolism. We drop our pH when we're doing more metabolism. We increase our temperature. We increase that 2,3 BPG byproduct of glycolysis, right? So all of those things happen when we're doing more metabolism, and all of those things cause a rightward shift. Okay. And so we have a rightward shift because of the lower pH, because of high CO2, and because of higher temperature and that higher level of the one of those byproducts of glycolysis, the 2,3 BPG. Okay. And so just real quick, with the people around you, just draw some lines like I just did. Use a partial pressure of 40 and just see what that does. Start with your blue line, right? And then see what a rightward shift would do to that. And then also see what a leftward shift would do to your percentage of oxygen saturation. Okay. And then kind of convert that from what it did to the percentage here to how we would explain that. We would say that we get increased unloading or increased loading or something like that. Okay. So go ahead, try that out, and then we'll come back together here in a second to finish up.
It's less of a.
Yeah.
So it goes.
You can, yeah, you can actually get the number.
Okay.
Just by, like you did there.
Okay.
Yeah. Mhm.
Yeah.
I mean, as straight as your lines can be. Line kind of shifts to the right, I'm noticing up there.
Lines. If you sign this, it'll increase in value to your entire.
Thank you.
Fertilizer.
Thank you, appreciate that.
But every
All right, let's go ahead and come back together here. Okay, so at that partial pressure of 40, I just drew a line straight through all three of them. It definitely shifts to the right. That's not the same kind of rightward shift we're talking about. That's just me not being able to draw a straight line. But it's kind of leaving it that way. But anyways, we can still kind of look at it. So with the blue line, what'd you get? Somewhere around 80%-ish? Yeah, so we're kind of the normal, the blue line would be about 80% saturation, right? With that red line, maybe somewhere around 50, 55. Is that kind of what you guys put? Something like that. So if we shift to the right, we got about a 50%, right? If we're shifting to the left, then we're up close to 95-ish, maybe 95%, right? And so obviously that rightward shift is going to decrease saturation, right? So decrease O2 saturation. The leftward shift is going to increase oxygen saturation, right? And so when we have low pH, when we have high CO2, when we have higher temperature, it means we use more oxygen to cause those things. So it makes perfect sense that we would want to drop off more oxygen too, right? And that's exactly what happens, right? We're dropping off more oxygen because of that, right? When the opposite is true, lower temperature, low CO2, higher pH, it means we're not doing as much metabolism. And so we don't need to drop off as much oxygen, and our red blood cell would not drop off as much oxygen. Okay, so the rightward shift would lead to increased unloading. And then we could say decreased unloading. But a lot of times where we see the leftward shift is at the lungs. And so then it probably makes more sense to say increased loading instead. That makes sense? Right, that leftward shift a lot of times is seen up at the lungs. And so then we're more interested in how it helps us with loading versus affecting our unloading. Okay. All right. Questions on that at all? Okay, so then just a little bit of the explanation with that. You guys probably dove into this a lot with biochemistry on a deeper level. And so the Bohr effect, right, is a decreased affinity of hemoglobin for oxygen with decreased pH, which is closely associated with CO2. Right, and so it has to do with maybe you guys tell me, what does it have to do on the biochemistry side? What's CO2, what are hydrogen ions doing, right? They're binding to probably some amino acids, changing the shape of the hemoglobin in some way to where it can't hold on to it anymore. Is that what you learned from Dr. Jansma? Yeah, right. We're kind of just like slightly altering the shape of that hemoglobin where it just doesn't have the ability to hold on to oxygen as well, right? And so, yeah, so all of that is there. Perfect. Okay. And then myoglobin, did you guys dive into myoglobin at all with Dr. Jansma? Yeah, so that whole thing with much higher affinity, right? So oxygen is only released from myoglobin at very low partial pressures of oxygen, right? Because that plateau is just way longer, right? We got a much bigger plateau. The steep part doesn't really occur until maybe, something like 20 instead of 40, right? So it's just much different in the way that it holds on to oxygen there. And that helps it because it has to pick up oxygen after it's been dropped off from hemoglobin, right? So hemoglobin had to let it go, and then we got to still get it. So we need it to have a much higher affinity for oxygen than hemoglobin. So, okay. All right. Well, let's just finish up with this little recap here, and we'll be done. So go ahead, fill this in, and then we'll go over it, and we'll be done.
The closest. Just anything solid. Something. Lung collapse. This is a baseline ventilation. A little more than that. Can't breathe. He is. I guess it depends what life is. The reason why it's low is so it's like should be like sound of fun today. So I appreciate tissue, appreciate so no reason to be I can go back.
Basically, it's being oxygen. Make sure that
Was that a CO2 measurement device?
yeah.
Okay.
Make sure they're breathing out.
So you measure it in the lungs?
Yeah, like when we kids came in with like a broken arm, and you had to put it back in. They'd be able to give them. I think it was mostly ketamine for kids. Older people those have to measure it to make sure they're.
Oh, because is it to the hyperventilate or do they? Oh,
they just stopped
oh, because of
breathing.
the drug. They
Yeah,
stopped
they
breathing.
couldn't, yeah. So you'd see like the CO2 waves.
Hmm, wow,
Yeah.
that's crazy. All right. Here's my version of the answers here. So V to Q, if the V to Q ratio is high, then this means we got ventilation but low perfusion, right? So this is a vascular problem of some sort. This could be pulmonary embolism, arteritis, fibrosis of the lungs, tuberculosis would cause this. If our V to Q ratio is too low, means we have perfusion but low ventilation, right? So some kind of issue with getting air to the bottom of the alveoli. Right, so emphysema, asthma, chronic bronchitis, pneumothorax. And then the two shifts, right? Rightward shift would increase unloading. That's caused by high CO2, high hydrogen ion concentration, low pH, high temperature, high 2,3 BPG. Leftward shift would cause lead to increased loading. Then we would commonly see the rightward shift at the tissues where we're doing metabolism. For the leftward shift, we commonly see it more at the lungs, and it's just kind of the reverse of all of those other things. So, yeah. Questions? Yeah, Daniel? Exercise or really any tissue that's increasing metabolism. Yeah, doing could be in your digestive tract, right? For Yeah, it would just be not using that area much. So just a lack of use of a certain area, then we don't need to drop off oxygen to that area. Yeah, we'll talk about an example of a leftward shift at altitude next week as well. Another thing that happens when we start hyperventilating at altitude that drops our CO2 levels, and that has some positive effects for loading for us too. Okay, other questions? All right, guys. Good luck on the anatomy test. See y'all next week. I'll get those grades posted pretty soon. I'm close. So, okay. Have a good rest of your week.